Okay, I always say this, but the best place to start would be the slides. If you're going to focus on one thing, just go through the slides, go through the practice problems you did in class. I've gone through and bulleted the major points, but honestly, I got these points by going through the slides, so it just makes sense. Take this, set it next to your slide set, and you'll be able to follow really well what the topics are that you need to know. For thunderstorms and tornadoes, chapter 14, understand, first of all, what conditionally unstable means. That's when I was describing what kind of environment you need to have for thunderstorm development, a conditionally unstable environment. So that's when you have cold, dry air over warm, moist air. The reason that's great for thunderstorms is that once you have this parcel that's warm and moist and something triggers it to go up, it's going to continue to go up. So you remember I used the water balloon, the balloon in the water to show you the buoyant force where I held it down and when I let go it just went up. The same with that parcel of air. It's going to be more buoyant than the surroundings, so in a conditionally unstable environment it will just keep going up. So that's the first thing to know. Second thing, know the ingredients for thunderstorm development. So that's just probably on the next slide. Maybe not exactly. But those three things: low level moisture, instability, and some kind of lifting mechanism. So the conditionally unstable environment is what I mean by this. Any kind of moisture, you need to have moisture in the low level so that when you lift that parcel, you're actually going to have cloud formation and then precipitation. Yes?
So, are you going through the chapters to break it down? Because all you have on here is just says test for review. So, you're going back through each one.
It's listed on the review though by chapter, the points.
Yeah.
Right. But she's going through the slides like that. So, are you want to...
Yes.
Okay. Gotcha. Sorry. Continue.
I don't understand, but I'm glad that you know what my answer is. Okay. No examples of lifting triggers. What are the different things that can cause that parcel of air to be forced upward? So y'all name some of them. What are some of the causes? Orographic features.
You want me to send you this video?
What's something that we talked about that separates air masses with different... Yes, fronts. Fronts can trigger upward motion. Those are two big ones. So fronts, diverging upper level winds, so when you're drawing air out, your air is coming in together. Really, terrain and fronts, you can remember those and be fine, because we didn't talk a lot about random turbulent eddies. Unequal surface heating, that's one that you can remember too, that when you have different areas heated differently, you're going to have thermals rising, and that can trigger upward motion. Okay. Understand the three thunderstorm types and characteristics of each. Do y'all remember the names of the three thunderstorm types? The first one I would always feel sad for because it was just called what? Kind of boring that it was called, remember? Ordinary.
Oh, yeah.
First type was ordinary. The second type is multi-cell, and the third is the supercell. So you have three types. Some basic characteristics. Which of those three is the shortest lived? Remember? Ordinary. And why do ordinary thunderstorms not last for hours and hours? Something about their structure. So what's feeding the thunderstorm? The updraft. So if the updraft is what is the fuel behind it, how do you kill it? You cut off the updraft. With an ordinary thunderstorm, it's just a vertical thunderstorm. So once you have a downdraft that forms, when you have that condensation occurring, you have big raindrops that are falling down, then that cuts off the updraft. So ordinary thunderstorms are short-lived for that reason. Let me go show you. So this is kind of why. Here's an ordinary thunderstorm. It has no wind shear, and we'll talk about that in a second. And so the downdraft cuts off the updraft. Whereas in the multi-cell and the supercell, you have a tilt to this storm, and so this downdraft where you have rain falling is separated from the updraft, which allows that storm to continue to last a lot longer. What is wind shear? Who remembers what vertical wind shear is? as you go up in the atmosphere, what happens to the wind in a sheared environment? If you're not sure, this would be a great slide to study. So a wind shear profile tells you how does the wind change with height. So here's the surface, and here are different pressure levels throughout the atmosphere. For a no wind shear environment, which is for simplicity, we're going to assume that ordinary thunderstorm has no wind shear. So as you go up in the atmosphere, there's nothing pushing that storm over. So it's just straight up and down, which is why it doesn't last long. However, in the multicell and the supercell, we do have wind shear. Speed shear is when you just have a change in the wind speed with height. So these wind vectors are getting longer and faster as you go up in the atmosphere. Directional shear only is when you just have a change in wind direction, but you'll notice all those barbs are the same length. And then speed and directional shear, which is what we have in supercells. Remember that speed and directional shear. Those are when you have wind speed and direction changing height. And so that allows you to have a rotating mesocyclone as part of the supercell because as you go up in the atmosphere, the winds are beginning to circulate with the changing wind direction. Okay. So that was this one, understand what vertical wind shear is and how it affects the storm type. Know the features associated with each stage of ordinary thunderstorm development. So this is the slide where we had 3 different stages: a growth stage, mature, and dissipating. So what feature do you see in the growth stage?
Updraft.
Just an updraft. Only an updraft, not a downdraft. The mature stage has up and down, and they're separated. Well, not in this case because it's one down here, but it's showing us there's the formation of a downdraft. And the dissipating stage is only downdraft. So remember those 3 stages and what features are present. Okay, be able to identify the multi-cell features mentioned on the slides. This will show up some in the matching section, but being able to walk through some of these different multi-cell features and recognize what they are: the overshooting top, gust front, shelf cloud, roll clouds, outflow boundary. So being able to distinguish between those various multi-cell features. And which feature, Scott can tell us this, which feature poses the greatest threat to aviation? Chris. I'm sure Scott can too. Chris can tell us.
Microburst.
Yes, microbursts and downbursts. Man, I'm sorry. This is why I just discovered, like 2 days ago, there's this awesome, what is it called, roster, like a picture roster, and it has all of your faces, and I would have loved that, I don't know, 2 months ago. So that's my way of making an excuse for
On
not
our
going.
IDs? Yes.
Huh?
Yeah.
Pictures.
Some of y'all look so different.
I've seen your ID. Funny.
My head is like this, stretched.
I'll be sure to look that up later.
Good job, Jennifer. It looks like I have a giant forehead.
Okay. Know the definition of a supercell thunderstorm and what makes it unique. So what do you know about the updraft of a supercell that is not true of the other 2? It rotates. So it's a rotating updraft. That's super important because what can form from that rotating updraft? Yeah, the mesocyclone is a big rotation of the updraft, and then what can form a really localized area? Yeah, a tornado. So tornadoes can spawn off of that rotating updraft. Know the process from wind shear to vortex tube to tornado. Anybody want to take a shot at explaining that? How do we go from a wind sheared environment to the formation of a vortex tube to a rotating updraft?
Starts out like flat, it's rotating on the ground, just around.
Right.
Vertical or horizontal. And then it changes, like, doesn't the wind shear start changing direction and it pulls it up?
Well, if you have the start of like an updraft, so something that triggers upward motion, it pushes up on that tube.
I can see the picture.
How about we just look at the picture?
My hand.
I I can't see the picture, it's like vertical, and then it starts pulling it upwards, and then or it's horizontal.
This picture?
And then it's vertical, yeah.
So you have this tube, imagine this tube that's rotating, and then all of a sudden you have some sort of mechanism to trigger it to go up. That forces that tube vertical. So now the tube bends upward, and you have on the backside of the storm, you have this rotating updraft. So that's what gives you that rotating
What
updraft.
mechanism forces it, I forget, forces it up though,
Just an updraft.
just any.
Yeah, any kind of, like there's
sudden, like, whatever.
any of those mechanisms, yeah, can trigger that to start to be pushed upward. And then if you remember the conservation of angular momentum, that was the ice skater demonstration. So as she pulls her arms in, what happens to the speed of rotation?
It's faster.
Yes, and so with the tornado development, you'll have a rotating updraft in the thunderstorm, and that as that updraft is stretched and it becomes thinner, then the spin increases and the rate of rotation increases, and eventually you can have a tornado development from that process. Understand the basic features of a tornado, know what a hook echo is, what a tornado vortex signature is, and how meteorologists identify the vortex and the mesocyclone using radar. So let's look at the hook echo. Echo, why is it called echo? It comes from a radar echo. So the hook echo is just an echo that looks like a hook. So it's in the backside of the storm. It's where the rotation of the updraft has started to draw some of that precipitation into itself. So if you have the rotation, here's the updraft. So imagine it's coming out of the page, it's part of the updraft, but it's rotating. So it's kind of grabbing that precip and pulling, wrapping it into itself, and that's where you can see. That's what allows us to see that backside of the rotation because it's pulling precip into it. And then this image on the right is from radial velocity. So this is where the radar is able to measure if there's an object coming towards it or going away from it. If there's anything rotating, if something's sitting here rotating in front of me, part of it is going away from me and part of it's coming towards me. So the radar is able to see that, and so they can identify circulations by looking at those particles. So when we have red and green together, that indicates you have winds going away from you in the red and coming towards you in the green. So there's a rotation here with this storm. Does that part make sense too? Okay. Understand why lightning occurs. It has to do with charges and the separation of charges. And how can you estimate how far away lightning is? Do you remember the rule?
5 seconds.
5 seconds for every,
Where did you see it? Oh,
for how long?
For every mile?
For a mile. So if it was 10 seconds between when I saw the strike and I heard the thunder, it would be how many miles away? 2 miles. So remember that little conversion? Okay, I listed some problems to go through if you'd like. Chapter 15 is hurricanes. First, just know the basic wind pattern in the tropics. So here in the U.S., typically winds are from west to east. What's the pattern in the tropics? The opposite. So it's from the east to the west, which is also called westward, headed towards the west. What is the name of an area of low pressure that occasionally triggers hurricane development? The very first thing that happens in this whole hurricane life cycle, you have what kind of wave? Remember the name of it? It's an easterly wave. So if we go back to the lecture. You have just kind of a little easterly wave that starts to come from the east to the west and creates an area of lower pressure, and then you can have convergence in that area, and that is the beginning of the hurricane life cycle. Understand the basic structure of a hurricane and its features. So that's like the eye wall. What do y'all remember about the eye? Tell me some of the eye features. It's calm. How about the temperature characteristics? What compared to other parts of the hurricane, is it warmer or colder? Warm. And do you remember why it's warm? When we were talking about circulations for climate, we said the really warm areas of the globe are because of what? The subtropical high. And what kind of motion do we associate with high? Sinking. So same in the hurricane. You have this eye that's warmer than the surroundings and clear because you have sinking air within the eye. So the air is going from a localized area of low pressure or high pressure down to the surface where we know the low pressure center is. And so, so you have an area of high pressure here, so that because of the pressure gradient force, so that's like a while back, high to low pressure, you have air sinking, and sinking air is not conducive for clouds. We get clouds with rising air, so you have a clear eye that's warmer than its surroundings. How about what happens to pressure as we go in towards the center, towards the eye? Does pressure get higher or lower? Lower. And it's at a minimum within the very center of the hurricane. How about wind speed? As you go towards the eye, what happens? Winds get faster, but then after you leave the eye wall and you enter the eye, then the winds drop off significantly. Understand what fuels a hurricane and have a basic understanding of the ingredients necessary. So this is the slide where I had big red letters in the top. Well, there's the ingredients. So you need warm surface water. You need it to be a deep layer of warm water because otherwise, as you start to have winds, you're going to mix a lot of the cold water up. You need to have winds coming together. The ones that we have not really talked much about, I won't expect you to know, like the weak trade wind inversion. And one of the big ingredients and the kind of the driving force behind the hurricane is this conversion from sensible to latent heat. So sensible heat is something you can sense and measure. So you can take a thermometer and put it in the ocean water and measure the warmth. Latent heat is the heat that's released when that warm air eventually rises and condenses, and condensation releases heat. So that process of converting warm ocean temperatures to latent heat is one of the big driving forces behind a hurricane. Understand the stages of development of a hurricane. Those 4 stages where we start with a tropical depression, and then we go up to, disturbance, then depression, then tropical storm where it receives its name, and then the hurricane. Know how to determine which side of the hurricane has the strongest winds when you are given the storm's direction. And I feel like y'all got this really well. This is a slide where we looked at circulation around the eye. And so on the eastern side of the hurricane, you have winds going north, and this storm is also moving north. So on the east, you have the storm's motion plus the wind speed. So the winds will be the strongest on this side and the weakest here because your storm motion is opposing the wind motion. However, if that storm would change directions, that scenario would change. Then you would have storm motion here, and the winds would be going west on the north side of the hurricane, so you'd have the strongest winds here, the weakest here. So be able to look at a hurricane and then understand where the strongest winds would be. Honestly, if you would just go through the problem we did in class, these 2 slides, just be familiar with that, where we went through and we talked about where are the strongest winds. We also talked about storm surge. So the storm surge would typically occur in like the right front region. So if this hurricane is moving due west, this would be the right front region. So just imagine as a hurricane spins, it's like gathering lots of water with it, and then it just pushes that water into the coast. So know kind of where the greatest storm surge occurs. And then just know there are different threats that are posed by a hurricane, and then we just talked about the storm surge. Any questions on hurricanes? Okay, this is my least favorite. So climate change. understand some of the possible causes of the past variations that we've seen. Those were, we talked about sunspots, we talked about the Milankovitch theory, do you remember that? Where changes in the Earth's wobble, in the Earth's orbit, and the angle, the tilt of the Earth, those changes can be, we can consider those possible causes for the past variations. With the sunspots, if you remember, we said the greater the number of sunspots, the higher or lower the sun's radiation, the energy strength. Do you remember? Yes, so the more the sunspots, the greater the energy from the sun. And then understand the concept of a feedback mechanism and how to tell if it is positive or negative. So a feedback mechanism is the idea that a change that has been initiated will be reinforced if it's a positive feedback, or it will be opposed if it's negative. So that was, let me find this slide. This one. So we talked about greenhouse gases lead to warmer temperatures. So there's the initial change. Temperatures are warming. Now, that allows for more evaporation. More evaporation leads to a stronger greenhouse effect because water vapor is a greenhouse gas. And then stronger greenhouse effect means warmer temperatures. So that's a positive feedback mechanism. A negative feedback mechanism would be that more greenhouse gases means warmer temperatures means more evaporation means more clouds. More clouds actually reflect more radiation, which cools at surface temperature, so that's a negative feedback mechanism. Do you understand the difference between those? Okay. Let's see here. Almost done. Understand the greenhouse effect in which gases are greenhouse gases. Then where do climatologists expect future warming to be concentrated? Do you all remember this? What part of the globe do we expect to experience the most heating? The poles. So the polar regions would be where climatologists would predict we would see the greatest effect from increasing greenhouse gases. And then understand the potential consequences of global warming. So not a lot there, and I feel like you probably know the answers to most of those, so you're welcome for doing a really bad job lecturing that day. Okay, chapter 17, this is today. Understand the different sizes of climate regions. We talked about micro, macro, meso, and global. Be familiar with the controls of climate. Those are the things like proximity to water, latitude, the 7 different controls that we listed. Know the forces behind the global temperature and global precip patterns. So we said, the main force behind the temperature would be latitude, because of the sun's angle in those different areas. For precip, or also subtropical high, where you have sinking air, that's associated with warmer temperatures. And then for precip, we said the ITCZ, where you have air coming together that's warm and moist, you can have higher precip. And then drier air with those subtropical sinking, areas of sinking air. And then, the Köppen system of climate classification. So group A is
The Great Vacation.
the Great Vacation in the what? Tropics.
Tropics.
Group B is
Bone.
bone dry in the desert. Group C is what we see here in Dallas, so that's the mid-latitudes, mild winters, moisture. And then D is discouraging, dismal, cold winters. And then E, even colder, and that's the polar regions. And then H, highlands. Okay. And so you guys have that down, and check that off. If I give you a chart of precip and temp, like we did today in class, you'd be able to tell me which group it fell within. And know which group is most prevalent globally. Do you remember that?
B.
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 Anybody have a cool way to remember that?
I just think deserts, because it's weird. The deserts, it's kind of sad, but deserts would be the most,
Yeah.
it's sad. Like, where's the fun?
Everybody likes deserts. Like desserts.
Ah, that's good. 2 S's versus 1, that's nice. Okay, so there's some review questions you can look at. Any questions?
Can you explain the storm surge again?
Yes, of course.
15.
So if we look at this slide, if the storm is moving north, you can divide a hurricane into 4 quadrants. So there's divide it in half this way and this way across the middle. So you have your right front quadrant and your right rear, and left front. Because of the storm motion and the winds, you know, that's strongest on this side. And so it's, as the storm circulates, it's kind of gathering water and then pushing it. It's concentrating the storm surge in that right front region. So if this storm was moving this way towards the coast, you would have the right front region would be here, because we're dividing it this way and this way. It's moving that way. So right front is this part. And so when it hits the coast, the winds are pushing the water up onto the coast. Whereas on this side, winds are coming this way. So it's drawing water off the coast. It's all about the winds.
But the red arrow was in the south, that was pointing towards south.
If this arrow was pointing south,
Yeah.
then the storm would be heading this direction, so the right front would be here. So it wouldn't really be affecting land mass in this scenario, but the right front is always where we would see the greatest storm surge. Any other questions? So you should feel super confident about chapter 17, don't you think? Yes?
So what are we doing about our final exactly, or report test?
Yeah. Pretend like it's here at 5 on Wednesday, and then I'll send you an email when I figure out where it really is.
Alright, so just check our,
Yeah. And I will also email you about the review if you want to come to that. It'll probably be Tuesday morning.
Tuesday at 10 o'clock.
That's what I'm thinking. With my little sidekicks. So I don't know how that's going to go. We'll be here. And y'all have been great. I've loved this. I don't know. I know there's been like lots of just interesting adjustments for you to make, but I appreciate it and I've really enjoyed it. Yeah. So
Probably learned a lot about teaching us.
what's that?
So you probably learned a lot about teaching.
Yeah. I wish I had more time. I mean, I had like a week's notice of starting, so I wish I had more time to like really develop stuff that y'all could do in class to understand things better. But I mean, hopefully none of you will have to retake it, so you won't have to see how much awesomer it'll be in the fall. But if you do.
SMU for this class does a lab.